So then
Yes.
I can just play from the beginning. Is it
Yes.
okay now? Okay.
Yes. What I'm going to do is
So
to introduce you to the people, to the
okay.
audience, because you
Okay.
see what we are going to do is I'm going to tape this and then it's going to be uploaded in YouTube, and
Okay.
then it will go to YouTube, also to LinkedIn and so on.
Okay.
So we're going to do the work in that way. It's a little bit.
Okay.
Well,
Mm-hmm.
to the audience, well, it is a pleasure to introduce you to Professor Debabrata. He's a very distinguished scientist and an outstanding friend as well. And today he's going to talk about data science with COVID-19 disease. And well, Professor has a very impressive curriculum vitae, which you can find actually or ask if you want to know more detail about it. Well, I'm not going to take his time because he has a lot of very important things to say to us. Nowadays, we know that this pandemic is still on and very aggressive. So I think the subject is quite appropriate. So, Professor, you are more than welcome. Thank you very much indeed. And you can start as soon as you want.
Okay. At the outset, I would like to thank Professor Roberto for giving me again an opportunity on this platform to tell about the other sides, what is data science and how it can be uh, taken care with the COVID-19 disease. So, because I am very much fascination towards the development of the data science with the data, wherever the data goes. So scientific study of the data is most important because interpretation of the data is very much important to know about the science behind it, or you can say that if the science can be brought back into a technology, we can bring a name of the data engineering rather than data science. Let us see that how we can go towards this, especially this set of data, that is COVID-19 disease. So I have kept my presentation in this forum that will be describing about the concept of the data science. Then we can describe some structural concept of the COVID-19 disease, which will be embedded with some epidemiological model. Then we will see that how data science can be brought back into this epidemiological model. So far it's called the data-driven predictive model. And then we can discuss about the new domain, that is the how uncertainty can be quantified in this kind of model with the help of the data science. So obviously, and this type of model, like the epidemiological model, will be uh, calculated with our performance evaluation of the epidemiological model based on the computation of the R naught, and these are not, we will be describing about some machine learning technique, which is one of the next generation matrix method, and then we will conclude the session. Okay, so first of all, let us see what is data science. So data science, as you are seeing, that is applying advanced statistical tools to existing data to generate some new knowledge. Okay, then along with that, in addition to this, we can also make you need a service change. That is, you convert the new data insights into changes to business process. So you apply the data science and then you add with that service change. Then all these things together, you bring into a smarter work, or whatever you try to develop, that should be smart, so that it will be more efficient and effective use of staff and resources. So therefore, data science with the service change, we can bring back into a smart work. So whatever the smart device or smart algorithm or any kind of smart process is there, we can always say the backbone is the data science. So we can define the data science like this. Data science is the science which uses computer science statistics and machine learning, visualization, and human-computer interactions to collect, clean, integrate, analyze, visualize, interact with data, create data products. So that means basically the data science is a multidisciplinary, because you need to have to understand the computer science part, of course, statistics, and along with some mathematics, and then machine learning technique. And visualization, computer interaction always will be there. So therefore, we can say that decision data science is an area that manages, manipulates, extracts, and interprets the knowledge from tremendous amount of data, which is very, very essential, because every time we know the data we are generating huge in all domain, but we are lacking of the interpretations. If we are not interpreting, then the further generation on which direction my experiment or any kind of measurement systems device will be developed, that will be unknown. So that is why interpretation is very much important. Again, the data science is a multidisciplinary field of study that I showed, with goal to address the challenges in the big data. And remember that whatever the data we have in our hand, it is basically a big data. Earlier, if we go back from today onwards, at least some 20 years back, there also we are having the data, but we were never used to call it as a big data, because that data was limited in number and not multidisciplinary oriented. So therefore, each and every individual subject or each and every individual experts, they were handling the data according to their science or engineering knowledge. So we can say that the data science principles apply to all data, that is either maybe big and small. Once you are having a big cat, you can always try to deal with the small cat also. So therefore, data science principles apply to all sorts of data. Data may be a big, maybe a small. Coming back to the same domain, so we can say that the data science invites various modes of analysis. One is predictive analysis, which in terms of machine learning, we call that a supervised learning, where we discuss about some ordinary least square regression and logistic regression. These are the very useful algorithm to have the predictive analysis of the data. That means you can develop a forecasting or forecast model. Then we have the prescriptive analysis, and prescriptive analysis works on a data set, and that determines what actions needs to be taken. And remember, in the prescriptive analysis, you have to have the idea of the optimization, because prescriptive analysis goes to the optimization route. We may have the forecasting model, but that forecasting, how reliable, how optimized is, that will be sufficed by the prescriptive analysis. Then, of course, we have the exploratory data analysis if the data belongs to a time series. That means the data we have captured with respect to the event of the time, like rainfall, earthquake, or any kind of ECG, you can say, EMG, MMG. So these are the time series analysis. That means with respect to the time, data is captured. Any kind of data coming from the sensor with respect to the time is also known as the exploratory data analysis. Then we have to have one more analysis called data envelopment analysis. So therefore, data science invites these algorithms and this kind of analysis. Okay, just note it down: predictive analysis, prescriptive analysis, exploratory data analysis, and data envelopment. So we can say, as a visual definition, how the data science looks like. So you have a machine learning where you have a hacking skills, and you have the another domain called substantive expertise. And when these two together intersects, you have a data science domain where you can have some traditional research and this kind of danger zone. Why danger? Because you may miss out some information, and then of course machine. So that means that you need to have a substantive expertise with a knowledge of math, statistics, and hacking skills, so that by use of the machine learning and data science, we can do that. So therefore, this is the definition of the visual sense. It is an intersection of the hacking skills and substantive expertise. So what is the goal of data science? Goal of data science is that you turn your data into data products. So this is a very important part, because product you are getting with the help of the data. So therefore, our basic goal of the data science should be we convert the data into data products. Data products in the sense some kind of meaningful uh, interpretation. So you can see that there are some data products from the Kaggle. Is a Flight Queen 2 is a flight optimization, then tracking Santa's slice, fluoro forecasting, Galaxy Zoo, and dogs versus cats. So these are all available in the machine learning model based data science product. Then we have the NIC, which is a pre-pilot data science evaluation, and which are likely to be incorporated to be a part of some labs or final project. So these are just examples of the why data into a data products. Then we know that all around we have the data. As I mentioned here, lots of data is being collected and warehoused. Warehoused in the sense that you are segregating the data in a various platforms. For example, that you have web data, e-commerce, you may have the financial transactions, bank or credit transactions, online trading and purchasing, social networks. So everywhere you have a plenty of data. So therefore, we can say that all around we have the data. Now, the question is that what complements the data science? We can do something on the data science, but what complements the data science? You see that there are various approaches for doing. One is performance management, evaluation, policy analysis, open data, and data science service. So we can say that the all approaches that can lead to service improvement, and it's about choosing the right tool for the job. Okay, you can combine also many of these approaches. Okay, for example, that you can combine policy analysis and open data. You can combine the performance management and policy analysis. So like that, then you can have the data science also. Second is that what contrast it does. If you take that the contrast is my business intelligence, so I can say that the business intelligence subject, but that is contrast with the data science in this way. In case of the business intelligence, we generate the query about the past. But in case of the data science, as contrast to business intelligence, we generate the query, the past, present, and future. So therefore, we can give another name of the data science. Data science provides the knowledge of a triplet, that is past, present, and future. There are plenty of researchers going on how the data science can brought back to the past, of course, the present, and in future. So therefore, going back to the from present to past is a challenging task, because you may not be having, basically in case of the image domain, it is required to know that the present image from their present image to link back to the past and the future, what could be the scenario. So this is a business intelligence part. Here you see that there are many kind of business intelligence contrast to the data science. And then another contrast is machine learning. If you look at one side machine learning and one side data science, the contrasts are like that. In case of machine learning, we develop new models. And in case of data science, we explore many models, build and tune the hybrids. Okay. In the second case, if you see that in machine learning, we prove mathematical properties of models. But in data science, we understand empirical properties of the models. Okay. And in machine learning, we improve or validate on a few relatively clean or small data sets. But in case of the data science, we develop or use tools that can handle the massive data sets. So in case of machine learning, we publish a paper, but in case of data science, we publish a paper, but we take some action before publishing. So these are the contrast between the machine learning and data science. And we all know that the backbone of the data science to develop something is machine learning. Without that, data science cannot grow faster. So therefore, we have to know that what are the machine learning models with their corresponding algorithms for various data sets. So we have a logistic regression algorithm. We have the naive-Bayes algorithm. We can have supervised machine learning algorithm, decision tree algorithm, support vector machine, artificial neural network, and deep learning, where we have a multi-layer perceptron, recurrent neural network, convolutional neural network, and hybrid. We can also have a hybrid model of all these algorithms depending on the objective of the data to be handled. So again, when you try to do that, the question comes that what is in the data science toolkit? You have a statistical methods, you may have a tools and user experience research. Now, in case of the statistical method, the sentiment analysis is one of the very important aspect for carrying out the data science job. You have a time series analysis, and then you can have a data mining. And other things also are there. You have a multi-level modeling, survival analysis, and A/B testing. This is one of the important part of the data science. Without this, it will not go. Just as a bifurcation, we would like to notice that A/B testing is basically nothing but that whatever the present scenario you have, that is your A. Now, if you modify that, it will be the B. Now, question is that which one I should accept or which one I should recommend, the present one or the past one. So that is the meaning of the present part. And depending on that, we can recommend the future part, or we can do something on the future. So therefore, A/B testing will be nothing but the present and past, and accept one, depending on the statistics behind that. Then we have a machine learning. You can have the propensity score matching, and you see that you have a logistic, multinomial. So huge amount of these things can be there. And if you look at in the data mining, you have a classification and clustering, principal component and factor analysis, forecasting, network analysis. So a huge amount of tasks can be there in the data science toolkit. So in the toolkit, if you just go towards this big task, that is statistical methods, tools, and user experience, then you can see that these various toolkits are there. In the case of the languages, we can use Python at the top. Then we can use the R. We can use the SQL, JavaScript, and Node.js. We have the various libraries in the Python. As we know that these SciPy, these are the common to many people. And in case of the data engineering, we have this kind of system like job notices, APIs, optimized data, pipelines, and so on. In case of the visualization, we can have the various types of this tool, like ggplot2 is very applicable for plotting the graphics or visualizing the data in our platform. So these are the data science toolkit. So therefore, we know that the fundamentals of the data science. Now the question is that where does the data come from? That means where from we will get them the data. So data may come from the happening all online, like we click, add the impression, billing the event, first forward, server, whatever the actions you will take, it will generate a set of data. Then you may have the IoT, that is Internet of Things, and these are the shorts. And then you can have the healthy or scientific computing to generate the data, or you can have the user generated, that is web or mobile based data you are generating, like YouTube, Facebook, Instagram, Twitter, everything you can use as a social media and generate a lot of work or a lot of data, so that we know that the data will come from the various resources. And then you can finally say that the data is my new oil as a World Economic Forum, and these are the various way of it is just giving the blooming of all the data. So whatever the data sets we have, we can segregate in terms of 5 V's and named as a big data. First is the raw data, which is a volume, then change over the time, that is the velocity. Then you give the type of the data, which is a variety, and then you define the quality of the data, which is a veracity, and then you process the information for some kind of decision, or making some decision, and which is a value. So you have the 1, 2, 3, 4, 5. So 5 V's will give you the life of the data. Without the 5 V's, you may not be in a position to analyze your data. So therefore, you can say, what can you do with this data, which is a big data? We can do that with some kind of traffic prediction and earthquake warning. So these are the two examples I mentioned. Of course, you can also handle the complicated disease or infectious disease, which I'll be telling you with a couple of slides and show that the results, how it can be. So this is, you can see that it is a crowdsourcing. That means you can do a cloud modeling or the crowdsourcing. Then you add with some physical modeling. You sense it by some sensors, that is some measurement devices, and whatever the data you generate, you assimilate the data. All these actions, when you will sequentially do, you will be able to produce this kind of thing. Some kind of app on a mobile to predict earthquake with a map and to show about some kind of city. So that means this kind of product, that is why I mentioned that the data you turn into a data products. Okay. And this has been quoted from this Alex Bain, UCB, who is the Director Institute for the Transportation Studies. There may be many other studies where you turn your data by doing this kind of task to a product. So again, now we try to represent that, as my talk is mostly the data related to the COVID. So we try to know that COVID-19 data set is also a very large in size and dynamic. That means it is daily changing with a huge amount. That means velocity is present, volume is present, and it is worth to process the data, and a lot of uncertainty is there, and various types of data comes. Some types of data are pertaining to the infections, recovered, and then disease, then vaccinated, so variant, so huge variations are there. So the different, so with all these justifications, we can say that the COVID-19 data are basically consisting of 5 V's, and then they can be labeled as a big data. That is volume, velocity, variety, veracity, and value. So here in my talk, I will be just describing about the uncertainty of this data. Means if I try to model the uncertainty, what information we can get, and then we will give some kind of structured or unstructured with the help of some predictive model or prescriptive model. So we can say that data science here generates a forecasting model to know the pandemic situation beforehand. AI and machine learning empowers the data science in industry level, social media, and in other environments. So data platform tracks the hospital bed. As you are knowing this thing, then we have to know about this side by side other environmental information with respect to this particular infectious disease, that it platform that they tracks you hospital bed capacity, oxygen cylinder availability, vaccination history during this outbreak, okay, COVID-19 outbreak. So we can say that whenever we have to have this type of model, any kind of data science model, you have to validate, because it is always questionable that how far your model is valid, what type of data you will be describing, and how far your data you have collected, and whether this model will be valid still if the new data comes. So therefore, all sorts of question comes to the analyst, who are the basically data analysts, because there are two types of people, data analysts and data scientists. Data scientist people will be giving your scientific discovery, and data analyst people will be doing the actual task where the interpretation will be there. So we have to have a validation of the data science models, which will be embedded with some machine learning techniques, takes place through some confusion matrix. So therefore, we have to know what is this confusion matrix. What I mean to say in this slide, that any kind of data science model should be validated through the confusion matrix. This confusion matrix will give you the idea that whether this model will be valid for how long, maybe 2 years, maybe 1 day, maybe that the 1 week, and like that. So we have to know that what is confusion matrix. Without this confusion matrix, if you try to sell your data science related product, I don't think it will be going to the market. So confusion matrix we should know very well. Let us consider a group with P positive instances and Q negative instances of some condition. And this confusion matrix is a basically 2 by 2 contingency table. Okay, if you look at this, here we write that the true condition, and here we write that the total population. So you may have a predicted condition, you are breaking into two parts. One group of population is predicted condition positive. Another group of population predicted condition is negative. So here you have that the condition may be positive, condition may be negative. So when you have the interaction between these two, you may have a product called true positive. You may have a value called false positive. And this false positive is known as a type 1 error. And whereas when you predicted condition negative, but condition positive, then you have a false negative, which is known as the type 2 error. And then you have these two interaction, which is known as the true negative. That is, so therefore, 4 events you are having. One is true positive and true negative. If you go diagonally, in the off diagonal, you have the type 1 error, which is false positive, and false negative, which is type 2 error. With the help of that, what we can do, we do the measure of the sensitivity and specificity. Now you see that the sensitivity and specificity, if you tag with your data products, automatically it will be having some kind of meaning. So true positive rate is defined by using this formulation, which is again 1 minus false negative rate. True negative rate you can define by this formulation, that is true negative divided by the sum total of the true negative and false positive, which is again 1 minus false positive rate. You can define positive predicted value, that is true positive divided by true positive plus false positive. And again, negative predicted value you can define by true negative divided by true negative plus false negative. So we can have the false discovery rate by using this formulation, and you can have false omission rate dividing by having this formulation. So all this quantification can be done by using the confusion matrix. In addition to that, as I mentioned, that sensitivity will be defined by this formulation, which is the number of true positives divided by number of true positives plus number of false positive negatives. And it will give you the probability of a positive test given that the patient has the disease. Many times, if you do not know that the sensitivity, you may land up with a false positive. That means a person is having not disease, but because of my measurement and not understanding the situation, we are giving the positivity test. So sensitivity will give you the probability of a positive test given that the patient has the disease. And otherwise, if you look at the specificity, you see that the probability of a negative test given that the patient is well. Okay. So therefore, sensitivity and specificity are the two important measures for any data science model. So now we can have these fundamentals of the data science. So we can go towards the data generation from this disease. These are all known to the many people by this time. So, but for the sake of completeness, just as a recap, we wanted to know that that this particular coronavirus is a RNA virus basically, and internal helical RNA protein nucleocapsid, which is surrounded by an envelope containing the viral glycoproteins. Okay, what is nucleocapsid? Nucleocapsid. This is basically a protein, and this protein is a phosphoprotein, which is complexed to genome the RNA. And as you know that the RNA is a single-stranded, and single-stranded virus is always having a huge speed compared with respect to the transmission compared to the DNA. So spike glycoprotein forms the large glycosylated prepolymers, which will character the coronaviruses. Many things are known to the many people. Those who are expert in the virology, they may be much more knowledgeable, but I have just captured with respect to my limited knowledge on this particular biological aspect. So we know that the virion will be called as the virus. So this is your nucleocapsid and RNA. So this structure is there, which is enveloped with some lot of proteins, spike protein we called. And then if you try to know that the coronavirus contain positive strand RNA with the largest RNA genome, which is approximately 30 kb. So therefore, the genome RNA is complexed with the basic nucleocapsid and protein. The difference between this RNA and DNA would be that it has having a uracil acid and thionine is not there. Other things are there. Okay. So that means DNA is a ATCG, and here there is that thionine is not there. Instead of that, it is having a uracil acid radical. So therefore, we can say this particular is having a variety of this kind of viruses there. And this is also having a type human coronavirus, which will be basically of this type OC43 and 229E, which are both etiologic agents of the common cold. Okay. Now, the viral life cycle will be like that only. During the infection with this one, we are infecting basically the RNA viruses, and then it replicates, takes place. If we look at it has having a multiple, that is 6 in the case of the MHV, overlapping, that is 3-inch co-terminal subgenomic. These are all biological informations. And why it is required? This is required to produce your vaccines. Okay. But of course, here in this talk, we will not go towards this because we have not brought into that domain at all. RNA virus is single-stranded virus where DNA is a double-stranded, and double-stranded means having an alpha helix file structure. So this is a complete your description about how it is attached to the host cell and damaging the disease. Okay, so these are the various kind of transportation, transcription, translation, everything is taking place. So therefore, having this simple information of this COVID coronavirus, we can say that the data science, how we can map into that. So data science, when we try to do this data, we have to need also to understand that the epidemiological models of the infectious disease, because just by the data, you will develop the data science model, but whether that model is really valid or not, that has to be encompassed with the epidemiological model of infectious disease. Let us see that the first study which I did with the help of this a model developed with respect to this data to test the epidemic model for COVID-19 of the Chile, where Professor Roberto stays. So we captured the logistic model depending on the data, and we compared the Italian epidemic curve. This logistic model initially we applied at the Italy and with a 99.96% accuracy, and then we again adopt with the help of this data from the Chile. Of course, the data we captured from the dashboard of WHO with their permission. And then this is my model. And here you see that the model predicts that the total contagious this person, which is a very at the early stage of the virus spread, and contagion rate, which could find it out, and peak of the new cases that time when analyzed, it was reached on the day of 36 of the epidemic. And these are the various your statistical methods applied, which is nothing but the ANOVA for knowing that the model performance. This is the sum of the square of the error, degree of freedom, and the mean square. This is the residual and the total of these two. And compared to that, when you try to go for a fitting of that, you may require the R square value, which I showed here 0.99, and adjacent R square is 0.99. That means it is giving a very good satisfaction of this kind of model can be well applied in case of the data which I obtained from the Chile and Italy. Okay. Same thing when this model we applied for the data on the China, we got this value, which was very, you can see that the date is there, 18th May 2020. When we analyze that with respect to simple epidemiological model, we will come out the epidemiological model for validation. And this was the outcome of the model, where we note that the R and R naught. R naught is the one particular quantity by which we understand the spread of the disease. We'll be talking about that quite a bit, which is value is 1.75, and the beta is my infection rate, which was 0.5647. Gamma is the rate of recovery, 0.323. This is the total number of populations we captured from the WHO website, and this is the endemic part of this one, and this is the starting point. And root mean square. So now you see that this was the prediction, and with the help of the data, and we were going up to this is my prediction. So prediction and actual model was almost matching, but there may be some kind of uncertainty which will be taking care of that. Okay. Then if you look at as a digital mode, these are my estimated model parameter. That means contact frequency beta we calculated, removal frequency, which was the gamma, population size, initial number of cases, basic reproduction number, like that only, all this. And then infectious period, which was the 3. That means after 3 days, a people was the infections occurred. And then final number of cases that time when I analyzed, it was there, which was the date I mentioned as the 19th May 2020, which was the daily forecast. And these are the other epidemic parameter of this model. Same way, when we try to do this model further, so estimated datum or the start of the acceleration, turning point, that means when you take a turn toward the further spread, start of the steady growth, start of ending phase, end of the epidemic, and end of the epidemic after the 5 cases occurred, after the 1 case occurred. So which was the date, and this particular date was exactly matched with a epidemiological model. I will showing that model, which model suits to the China data or any other country data. Okay, and these are your statistical parameter, that is degrees of freedom, root mean square error, R square value you see 0.99, and F statistics versus 0 model is showing that where it is giving that the p-value is this much, which is very highly significant. So that means model is really good. So again, the same model we applied for our country, and then we got the value of R0 1.40, and this was again on the 9th May 2020. So here in this case, you see that a lot of exponential rise. This is a cumulative data, so it was giving like this projectile. And when you try to go for the daily new cases, it gave me a Gaussian curve, which will predictive of the fall line of the 1st August. Okay, and there you will see that how it is really true, this model. So these are again that parameter R0, which is the one basic reproduction number, which is 1.40 here. Beta was the infection rate 0.316. Gamma was my rate of record, which is 0.225. So all these parameters it gave the result. And how do I obtain from the data? We will be discussing that. These are our again output list of the same parameter, because the model is same. So we listed as a file, that is contact frequency rate, removal frequency, population size, initial number of cases, and so on. Okay. So then the major point of knowing that what is the acceleration phase. So 23 days it took after 23 of the onset of the system being activated by this, it took the 23 days. The deceleration phase of the 25 days. So all this point you understood or you obtained with respect to this, with the help of this model. And the end of epidemic was 3rd October 2020, and exactly we got the 3rd October 2020, which was the first phase was over. And later on that the another variant came and it took the country to another danger side, which will be known as that variant was due to the Delta and Delta plus. I will show all the results. That is the data science beauty and outcome of the model. Again, you see that for our country, it was the number of observations to take 70, degrees of freedom are 66, R square value was important, which is a 0.97, and p value is very highly significant. Okay, so statistics again for the daily new cases, you see that the p value was 1.25 10 to the power minus, which is highly significant, and the R squared is again 0.99. So this gives your performance model is very much satisfactory. Okay, these are the with respect to the same that the database. Now we try to apply for the different other country like France. You see that we got the result as per the WHO plot, and then Italy we got this one. So they have obtained the peak at this on this day, that is almost at April, which I showed that they are also by the model. In the case of the France, we got almost like a May. This is the scenario, and the maximum value was infection of the maximum value was this. This is the UK, and this is the US. So you can see that almost they are shape wise. If you try to see, it is slightly higher than this UK. So these are the various confirmed cases of COVID-19 in India. The graph may be very feasible. It is gone exponentially increasing. And here also you see that when you go for the death profile is a lot of fluctuation and increasing exponentially. This is the observation from January to May 18, 2020. Okay. So this, in case of the China, the confirmed cases was again variation was like this, and death profile variation was like this. So at certain time there was no death at all, but at a certain time it was having a spike. Okay. So therefore, in case of the China, daily recovered profile was basically that. This data was also captured from the Johns Hopkins University. That's sort of thing I mentioned as well, because the authenticity of data should be there. Then in case of our country, that COVID-19 map, we plotted that. That means which are the cities are affected due to this coronavirus. And these are the statistics at the very beginning of the year of the 2020. And then we have this kind of thing. Now you see that that Maharashtra was maximum. So that is why in our country that was labeled as a hotspot. So this kind of labeling is also understood that you are not in a position to tackle this spread of the coronavirus. That means your administration is poor. So if you rank basically on the basis of death, the data science will provide you how your administration your state is. So in order to know that the administrations with respect to the break the chain, you will be always knowing. And that is why they apply the lockdown and many other things. So spread of the infectious disease, which was based on the R0. As I mentioned that the R0 is a very, very important point. So COVID-19 is a new infectious disease, which I know. It has got a lot of features to still to know that many features, because a lot of variants we have received. We have given that we have started at the alpha, then we came back to the beta. And we also know that there is the intermediate, the gamma variant, but not that much of this thing. Then we came to the delta variant and delta plus, and now present is the Omicron variant. Every variant has got its own characteristics. Like Omicron has the total number of mutations is 32. Some people call it 37, but it is basically 32 as per the genomic structure. Then more the mutations you have, your transmissibility is faster. That is the basic philosophy of the number of mutations and the transmissibility. So here in the new disease, you can say that depending on the R0. So if R0 is greater than 1, so disease becomes basically endemic. Okay. Sorry, if R0 is less than 1, this is a slight typing mistake. If R0 is greater than 1, it is spreading, but if R0 is less than 1, this is because endemic. That means if R0 is greater than 1, so your variant of concern or issues of concern should be taken care. Okay. So now the question is that how do I calculate the R0? Because when we analyze the data, when we do the data science part in the COVID, our aim is that we would like to know how fast the spread of this occurs. Okay, though we will be notifying, but theoretically how we will come to know as a data science part. So it is basically to compute the R0. The moment you compute the R0, which I showed that my earlier model, you will come to know. So the various methodologies are there to compute the R0. One is known as the attack rate, next generation matrix method, maximum likelihood method, which is a machine learning technique, Bayesian regression, which is again a machine learning technique, and next generation matrix method we adopt many places. And this method is what? This method is nothing but whatever your compartmental model you take, and that all the compartmental model, whatever the compartmental model you take, all this compartmental model, you can write it down in this form of a differential equation. And if we evaluate this with, if you take the derivative, so you will get the matrix called F, which is nothing but my rate of infection. And if you take the derivative of this B, we will get the rate of recovery, which is my matrix V. Having these two matrices, if I take the inverse of this matrix and product with that, we will get a product that the FV inverse, and the largest eigenvalue of this matrix will be my R0. That means a spectral radius, what we call. So that means to compute the R0 by using this method, we nothing but that. So therefore, the computation of the F and V and their derivative can be taken care by a different route of the data science. So we can, in general, we can say F is nothing but looks like this mathematically, V is nothing but that, and then R0 is the dominant eigenvalue of the matrix. And we try to know that the dominant eigenvalue, we can very well apply some different techniques, support vector regression or many other. One is the classification and regression trees to get the eigenvalue product by power method. Okay. So this is one model I am showing. This is the China model, and it is based on the susceptible, exposed, infected, and recovered. That is ACIR model. China model was the host and reservoir model, and this is the complete network. So it is coming from the bat and then how it is related. So this is a complete network structure of all the components. And now this network structure, if I try to apply, we will get a system of coupled differential equation, first order, and that differential equation we will generate in terms, means we will write in terms of this F and V matrix, and here is the V inverse, and this is the F matrix. I explained that what is F and what is V. So therefore, R0 will be equal to F and V inverse matrix, largest eigenvalue. Here the A and B, all these things I have defined. So next generation matrix method will give you R0, and this is your FV inverse. Okay, so you have to compute the eigenvalue of this method. So if the matrix is very big or very complicated, you can apply a data science route or numerical methods like as power method to get the eigenvalue. So this is you see that there is spectral radius of the FV inverse, which is nothing but R0. Analytically, if I do, I will get this result. And then after doing the data science model, when you get all these parameter values, then you substitute back, you will get that R0 value. And so with the help of that this expression, we calculate that the R0 from reservoir to people is 2.3, and that from people to people estimated as 3.58. That was the China strike, 3.5, almost 4 people, one estimate. Interpretation is that one infected people would infect further 4 people. That is the meaning of the R0 3.58. Okay. So therefore, we know that infectious disease epidemiology is nothing but it may be acute, that is the first infectious, and it may be chronic. Okay. If it is a chronic, then it is a stay for a larger period, or if it is acute, then you have a short period. For a short time, you can be isolated. That's all. So these are the various compartmental COVID-19 models. Basically, they are epidemiological models, but since we are mapping this model or tuning the model with respect to the COVID-19 data, so we can call them that they are basically a COVID-19 model. For example, quarantine conditions, if you adopt, it might not be there in this standard epidemiological model, but if you adopt with respect to your scenario, then you will have it. If you apply your vaccine, so you have another model called SIV. So therefore, this compartments model will be written in terms of a first order coupled differential equation. So the model success is basically a calculation of R0, and R0 we have calculated by using next generation matrix. There is another way of calculation by machine learning we can do, and then compare both the two. So here I have mentioned that if R0 is greater than 1, infection will spread until the herd immunity reached. And herd immunity basically defined as the 1 by 1 minus 1 by R0. And if R0 is less than 1, infection will die. With the help of the herd immunity, you can also calculate the efficacy of a vaccine. That means if you are vaccinated, how long that the vaccine will be there in your body to be effective with respect to the virus, you can easily calculate. And that way your herd immunity also can be judged. We are not bringing all these part details. So therefore, we can say that the initial constant of which is called the basic reproduction number, which is nothing but the R0. And this R0 we require to calculate, and because the R0 can be changed, so therefore we can say that the one RT, which is a dynamic variable, so RT can be mapped to the R0. We will show that the RT how it is mapped to the R0. So these are the variations already we shown, and in case of China we have shown that the first estimation was R0 2.6, then again after that it got changed. So how the changes took place by various authors? See, R0, somebody calculated 3.8, somebody calculated 6.47, 2.22. So when there are so many values of a single same parameter, then which one to be accepted? To know that how the spreading is occurred. So therefore, we have to do some kind of data science study in this case to accept that one. Okay. So these are the temporal profile of some kind of data with the China. You see that they have got the active cases like that. And these are the very few, and this was your temporal profile of the total cases that the exposed, infected, and recovered with the U1 data. Then again, you see that this is the exposed and infected both. And now you see that how the R0 with respect to the onset of their disease in their country, how it is gone changing with respect to the different population. R0 was 3.1, then it got 2.6, then it got 1.9. Our basic attempt to administration is nothing but to reduce the value of R0. The moment you are reducing, that means your administration is good, you are taking care of the people, and then you are going to free from this attack of this particular disease. So then the question is that how R is mapped to the R0. R is exponentially mapped to the R0. That means R equal to R0 into e to the power of gamma t, where gamma is labeled as a recovery rate. And this is the result for the graph theoretical model, which I showed is a and so this is a 1.75 result. Then again, you see this is the result for our country, where R0 was 1.40. Earlier the data we have shown up to certain thing. Now the data we have changed again up to the certain months, and these are again variations earlier we showed. So ultimately the model which is based on the data model, so I named my own name, and this is the complete network. So what I did, instead of taking the one single model, we took many of the models, and then this model we first captured with the data driven model, and with the help of the data driven model we feed into a simple SIR model, upgrade to the SIR, and this one we upgrade to a bigger model. So that means a very big network structure we developed, which is initialized by a data driven model. So if my model is wrong here, everything will be wrong here. So therefore the valuation or the performance of the data analyst or the data science driven model should be good, so that we can have a very good network structure. So we help of that, we try to model that how much uncertainty exists in the model. You see that there exists uncertainty in the epidemiological model. And uncertainty, of course, uncertainty is because of the veracity. That means how fast your data is coming and you are not able to capture, and how noisy that the data is. So uncertainty exists in fitting the model parameters from the real data, which is source 1. Uncertainty exists in making the assumptions of the epidemiological model, source 2. And uncertainty may present in the data itself as noise, source 3. So our aim is to look at here, which is the source 3, and uncertainty arises whenever transitions occur from this pandemic to infirmary. That means one variant came, which was not that much of serious, but people took it as a serious with the past history, and therefore it came back to the pandemic to infodemic. So we can have our forward propagation of uncertainty. That means we got the result, various sources of uncertainty are propagated through the model, or we can have the inverse assessment of the model. That means parameters are not known to me initially, which is basically for a data-driven model. But therefore, with respect to the optimization route, we can assign the uncertainty of the parameter, and then we can develop the model uncertainty. Okay, so that means you may have a forward propagation of uncertainty, or we can have the inverse assessment of the model uncertainty. So these are some of the results. Again, you see that the date changed. Earlier I showed that in May, now it has come to the 5th July, and it was giving the showing of the China result with this epidemic model, which was my own model. And again, we changed to the various models here. As I have not mentioned so far, these are the models which I took. SIR, I showed in the network, susceptible, infected, recovered. SIRD, which is susceptible, infected, recovered, dead. Each and every letter is nothing but a compartment, and they are connected. And how that connection, that is the network structure. ACIR, ACIRD, and ACIQRD, which is susceptible, exposed, infected, quarantined, recovered, dead. So all these things you can consider. And apart from this model, these are all epidemiological models depending on the situation. And then you can have your data-driven model. Data-driven model may be a logistic curve, Gompertz curve, or maybe a fractal model. Okay. So this is one logistic growth model, which I showed. And again, for the exponential growth, how it is. So this is my logistic curve, and this is my exponential. So for this particular thing, we wanted to map, so everything will be within this confined here. Okay. And these are the results of the China data, which is captured from the data-driven model by logistic growth formula. And then you see that when you try to do a logistic model, what data science does by a statistical technique, you read the data, you define the logistic function, you randomly initialize that parameter and set the lower and upper bounds, and then apply a statistical method called nonlinear least square method. So this is basically statistical methods of the data science route to develop the logistic growth model. So now, with respect to that, we developed this model. Since there was a turning point, so we got this. So these are the actual data which we captured by this. So therefore, you can easily find it out how much time it took from this achieve that. That is the 21 it showed according. And some of the Python program I showed here. So this is a Gompertz model again for China. This was the actual model for cases, and this was the death. The same thing you can apply for your own country and find it out that whether this model is true to interpret that how many cases in future will be there if this is the situation, and what could be the probability of the death. And this is the route. You see the various. Now you see when you try to do, there is a huge uncertainty present. Uncertainty here is meaning that from one domain to another domain, means one part to another part, if you try to do, how much will be the peak. So that is the meaning of the So blind test of uncertainty estimation on the China COVID-19 pandemic. The best indicator that the forecasted cases and deaths counts generated from the best fit Gompertz model, and low and high are the low and high case forecasts generated by adjusting the forecasted for the model up or down. So this is one simple model I tried to show for the sake of complaints how they are connected. So these are my compartment. Okay, and every compartment is coupled with a written in terms of the a differential equation, and this whole system, when you submit into a matrix form, you will get that the F minus B. And with respect to that next generation, if you calculate the R0, you will get this model as a beta by gamma plus mu. So that means for this model, R0 is beta by gamma plus mu. If I know that the value of beta from the data-driven model with a network structure, and if I know that the gamma and mu, automatically we can calculate that. And that sort of thing only we did in our model. So here again, to carry out the uncertainty, we have to know that what is my death projection. Death projection statistically again can be mathematically written into this. What is the probability of occurrence of this condition that here is there? And since we have taken the SIRD model, we can take that as a Gaussian with a mean 0 and sigma square is the variance. And this is the inequality for satisfaction of your uncertainty root for the death projection. And again, I'm not discussing because this is the mathematical route to go for to get the likelihood of my probability of occurrence. And then finally, if you do apply that, you will get your uncertainty result. So this is the figure example of a model fit to a full COVID-19 endemic wave of the China. And this is again the fit to a largest stage of the Italy. And this is the epidemic wave for the UK. So we got the uncertainty result. You see in the case of the UK, it was like that, though it is not much readable, but if you look at we can read that. I will show that some other results also for our country. So we apply the EDA and CDA, that is exploratory data analysis, confirmatory data analysis, cognitive analysis, and uncertainty. So we are focusing toward the uncertainty. We can also develop the performance-based study like which I mentioned listed here, that is MCDM or smart MCDM, and all ports that the fuzzy modeling we can develop for the data set that can be developed. These are all the research questions and research problems basically. So now some of this outcome I am showing, which is an early report as per the WHO, whatever that the WHO plotted, same thing we tested by our model to satisfy that. And then this is a scenario for up to 31st October for our country. Okay, with the same of this model, we got this value. And here I showed you that your beta value you got and gamma we got. And if I get this real value, and if these values are correct, then definitely I will be able to achieve my peak at the same day, which media also mentioned. Okay, this I already mentioned. At the initial stage of the outbreak, since R0 was greater than 2, and average infected person infects 2 or more people. That was the initial we observed. Then here what you do, this is a prescriptive data analytic model. Here the data are grouped. That means data grouping is done by confirmed group, death cases, and recovered. And this data we took from Johns Hopkins University, January 31st to October 31st. And on the basis of this analysis, we developed a prescriptive model by using the nonlinear least square optimization technique, which is a double Gaussian function. We try to fit that, and this is the double Gaussian function we fitted for our country for the infected cases, that is daily cases, confirmed cases. We have given that the level, and you see that the double Gaussian case, this is my model, it fitted, where the coefficients I mentioned here with a 95% confidence bound, where my R square value was 0.9877. And the most satisfaction of this model is that we obtained the peak on September 12, 2020. This is the first phase or first wave of this particular disease in our country. Okay, so that means with the help of data science, we try to get my model into this, and this model will give me whatever the number of functions, that is number of cases, that cases if we take in case of the epidemiological model, which I showed that the RD COVID-19, and it maps. This is again a death rate, that is daily death profile is nothing but my all the scattered point, which I modeled by using a single Gaussian model, where again a R square is 0.91, which a good coefficient value with a 95% confidence bound is giving A0 is A1 is 1062. The bounds are mentioned within the parentheses. B1 is 1.03 and C1. So having this, you can submit back into that, and then X, if you take the time, X is nothing but my time. So we can mention that at this particular time, what will be the number of deaths. So with respect to that, we need to calculate the case fatality rate, which is 18.25% is showing for this thing. And case fatality is nothing but the number of death divided by number of infections. So that is the epidemiological definitions of the case fatality rate, and which is almost zero, you see. And the number of days, if you count out, you see that now also, because of this high rise, the death profile is very, very small. So these are the outcomes, some of the outcomes. So many of the epidemiological outcomes we are seeing here. And what we did, we tried to break up on the different states to know that why so much of information is there. So first, Maharashtra we say, which is the input of you can input your name in my model, and state code you can just write, so automatically it will take care. Then it will give you the initial date of confirmation observed was 9th March 2020, final date of confirmation observed the 4th August 2021, and peak of the daily infection of the first wave occurred after 190 days from this 9th March, which, and the value of maximum cases of infection was this. So this many people were infected. And peak of daily infection for second wave occurred after 400 days from the onset of the 9th March, and maximum value was occurred this. So this model will give this information, and date of occurrence also it mentioned. That is the first peak we obtained on the 14th September, and date of occurrence of the second peak we occurred the 22 April. Now you see there is a certain correction. Initially I showed the 12th September, but when we further analyze, we got the 14th September. This invites there must be some uncertainty present in that I will show you. So these are the second wave and peak. These are the Maharashtra result. And detail you will get the result, how much of the contact rate, how much of the removal rate, and what is the population size of the Maharashtra, and initial number of cases. So all these things you get, and R0 value was 1.25 in case of the Maharashtra state in our country. So these are the various outcomes of this figure. This is your daily confirmed case of Maharashtra. This is the first wave, and this is the second. And now you see the height, the ratio of the height, if you calculate, you will see there is a 4 times. Everywhere it is a 4 times. So this is my confirmed cases. So therefore, this is the result of the Maharashtra. And now we try to fit the complete this thing. For this one, we have shown that the double Gaussian model. But when you try to do here also a double Gaussian model independently we are having. But overall, we may have the triple Gaussian model for doing this. So a good spectroscopic analysis can be done, and further variation may be slightly high. So if you take all these Gaussian peak, you can have a lot of information. So basically, this is a double Gaussian model for daily confirmed cases, first and second wave fit. And now you see there is an uncertainty, which I showed here. So this uncertainty we show here. And so we can say that in that earlier model, how that it looks like that. This is my infection rate versus the date wise, how infection rate was there. So it was go on doing that. We got the peak as per this model. We can predict also that when the situation will be normal. This is the case of the Tamil Nadu, or the 25 July up to 2021. And here you see that your date of arrival first peak was different from the Maharashtra. Similarly for second wave. So when the country is having so many different states, so administrations are not same. So therefore we can do a performance-based analysis in the optimization route to know that which state is following a best administration. Automatically administration goes to the chief minister of that state. So he or she may be the responsible for adopting the administration. These are the results is showing. And then again, this is the Andhra Pradesh, how the variation is showing. And you see that the Andhra Pradesh that we have got the first wave, and then actual predictions of the second wave. Okay. And these are the simple profile for your epidemiological model, time-wise how it looks like. And in case of the West Bengal, where I belong to, so initial date of confirmation observed was 17th March. Final date of confirmation observed was 4th August 2021. Peak of the daily infection for the first wave occurred was 221 days after 17th March. And all this information I have written here. Date of occurrence you can notify that the first peak we had got the 23rd October, which was exactly matched to the other society like ICMR or WHO also has provided CDC guidelines as per the other state people, scientists or engineers they calculated. So data of occurrence of the second peak as per my model it gave 13th May. During the first wave, peak of the daily death occurred 217 days from 17th March, and value of the maximum cases notified here this much. Second wave, how many people were infected, maximum case, peak occurred on 17th March. So now you see that how the first wave variation. Now everywhere, whenever such kind of thing, your administration or there may be some lot of uncertainty. And this was the second wave. And this way that my crude fatality rate is, mortality rate is decreasing. So you may not be having any mortality beyond this July or July 2021 or so. Obviously not, because in the month of March only it will be declined, provided that there will be no further variant to surge the system. And here you see that how my first variation was there, first wave peak, and this is the, and if you take the ratio again, you'll see that the 4 times, it was the 4 times. Now the situation will be towards maybe the 8 times with respect to this one. So this was, but what I mean to say, there must be uncertainty present into that. If there's uncertainty compute, it may be shifted. Okay. So this was the result of the West Bengal profile. And then these are again the total profile for the India, which was the earlier. So we have to look back from past, present, and future to know that whether the data science model is working or not. So now with the help of that, we try to calculate some uncertainty analysis. And uncertainty analysis, I mentioned that we will focus on the computation of R0. Okay. So this model performed quite well on Delhi. This is likely because Delhi is much more homogeneous in terms of the demography and is more well connected. And let us see that how the result looks like. So after 60 days, this is the city of the New York City. After 60 days, I took, after 68 days, and after 125 days. So these are my 3 days of measurement of the model, and we calculate R max, R mean. So this was the maximum to minimum. So this is the uncertainty. That means that the maximum side of the 60 days is this much, minimum was this, and 68 days it was this 2.3429, and minimum was 0.95, and after 125 days 2.4. This is the value for New York City. How much uncertainty? Based on that, we can do your other break the chain administration. This is for the Spain. You see that how the uncertainty was there. So initially when the peak arrived, the uncertainty can be calculated, and which was the result for 60 days after 68 days, and after 120 days. That means the more you passed, so your uncertainty will be maybe that they minimized. Okay, so that means you're tuned to the better administration. This is for Italy. You see that the 1.9158 after 127 days here I took, and 0.86. Okay. After 80 days, this is I think 80 days, you got the 1.9. So that means at Rmax value at 80 days and 127 days almost same. But in case of the minimum, so there was a little variation. So that means there must be some kind of uncertainty exist, and because of that, you see there is the overlapping all these things. Okay. So this is again for our own state, that is predictions with uncertainty intervals of Maharashtra. In case of the Maharashtra, you see that we took the 75 days, 89 days, and 103 days. Why the date variation? Because the data should be available, because nobody will give the data. You have to just repeatedly ask to get the authentic data. Otherwise, your calculation and model will not be giving the good result. So this is the uncertainty of the R max and R mean for this corresponding 3 days for the state of the Maharashtra in our country. This is for the Delhi. You see, it is quite, this is my projected, okay, and these are the used points, and these are the unused points. So R max and R minimum variation after 96 days, it was 1.4 to 1.13. So almost many minimized. Okay. So here you see after 110, this is for again the Delhi, 110 days, you got the 1.4 and 1.4. So that means you have almost brought back into the similar domain. So ultimately we can conclude that the data science with COVID-19 disease, we try to see that how best we can present or how best we can represent the data with respect to the various computations of R0, either by using next generation matrix method or many other machine learning techniques directly we can take from the data itself. And there are a lot of variants of COVID-19 we may face. As presently we are facing the variant of Omicron, but not to have the panic. So ultimate lessons we learned from this particular presentation, that uncertainty is one of the issues to be carried out when we do the data science. We should capture the data science, and we should have the data cleaning method, which I carried out, and then machine learning models should be properly judged by confusion matrix computation. And that's all. Thank you very much, Professor Roberto, for giving again the opportunity to tell something about my model as well as the situation in the global world. I may be wrong, may be right. That is, you are the judge, you can judge. But I got the result.
Well, I'm very happy having heard this talk of yours, which was really excellent. And I will remind you that we would like to make a tribute to your work you have done in our electronic magazine. So when you can, please send me some of the material.
Yes, sir, definitely.
For the next issue. And well, in that case, you see, people will get to know a lot more about what you have done and what they need to learn. And we all need to learn, of course.
Yeah.
You have a huge experience. My dearest friend, please do remind me to your family.
Yes, sir.
Stay well, and we're going to be in close touch as usual.
Yes.
And I hope that we will have a talk one of these days again.
Yes, yes. Some of the time we will have a talk, and we should start from the month of February, our spectroscopy book.
Yes, that's going to be absolutely wonderful. Yes. Well, it has been a real pleasure. Yeah, and I'm going to send you the link for the YouTube, okay?
Yeah, sure. Please. I will send you some of the material so that we can
start with
publish some of the article, your newsletter. Okay.
Yes.
Inglomer,
York. Yeah. Which is, well, we're going to wait for that. We're really excited about that. Yeah. So please do take care and be blessed, and all my love and affection to your family, friends, and beloved people.
And thank you very much from my heart that you are arranging so much of discussion, so much of this thing. You are really a very hard work at this age also. So age is not a matter at all. It is a simple number.
Well, I just try to follow your good example. Yes. I need to work hard. Yeah. Bye, my dear friend. Bye. God bless you. Bye. Yeah, bye. Bye. Take care.
Okay, sure, sir. Take care, you too.